Hey guys, welcome to Gamma Digamma.
Hello guys, welcome back to my channel. In this video, I would sort of like to continue the streak I started with the integral of 1 over 1 plus x to the fifth. Except this video will be a lot shorter and a lot less tedious compared to that. I hope you enjoy. Okay, so we have 1 over 1 plus x to the seventh dx. What I want to do is factorize the denominator. So to do that, we have let's find out the roots of this equation. Let's evoke complex numbers. So with e to the I pi, you can write -1 as this. You can write it as this. So you just keep adding 2 pi, 5 pi. We know by the fundamental theorem of algebra that there are 7 roots because the power of this polynomial is 7. So 1, 2, 3, 4, 5, 6, and the last one 7. So all I've done, I've just added 2 pi to each of them, which means you sort of keep on rotating in the complex plane. So one rotation gives you 3 pi, another one gives you 5 pi. So we'll keep doing this in the complex plane. That's all I've done. And now we can sort of take the seventh root on both sides of this equation to get the seventh roots as e to the I pi over 7, 3 pi over 7, 5 pi over 7, 7 pi over 7, which is just pi, and e to the I pi is -1, so that's the most obvious root. Then we have 9 pi over 7, 11 pi over 7, and finally 13 pi over 7. If we take 15 pi over 7, if we didn't know the fundamental theorem of algebra, if we took 15 pi over 7, for example, which is what you get out if you add another 2 pi to 13, you can write this as e to the I 14 pi over 7 times e to the I pi over 7. 14 pi over 7 is e to the I 2 pi. E to the I 2 pi is 1. This just becomes 1, and you basically return back to where you started. So the way I like to think of these things is a geometric picture, what's going on. So that's 1/7 of pi. So 180 degrees, which means pi is here. So 1/7 of this angle, somewhere about here, is pi over 7. You keep adding this incremental factor of 2 pi over 7, and then you finally come here back to where you started. That's what happens with, say, an eighth term, like 15 pi over 7. So that's just one thing to remember, or at least consider. It sort of validates the fundamental theorem of algebra. Plus, structures like these groups that sort of come back to where they started, we use these structures, these modularity property in the Galois theory to define Galois groups. So if you want to check more about that, you can. That's just related to stuff like this, finding the roots of polynomials. Let me just change my color quickly. Now, how is this helpful? Because now you can represent 1 plus x to the seventh as a product of these factors. So x minus e to the I pi over 7. This method is way more cleaner and way more compact than arbitrarily factorizing out. The factorizing method doesn't really work all the time, as I pointed out in the comment section for the fifth power video. But this is how the factorization will look like, because we've considered all the roots. So indeed, if you multiply them all together and massage the terms appropriately, you should end up with this. There's nothing wrong with this hypothesis. So since we have these 7 linear factors, what I would like to do is use partial fraction decomposition. So 1 over 1 plus x to the 7th. I want to represent that as some factor over the first term plus b over second, c over the third. It's a pain writing these out, and I think I missed a term here. I missed the pi over 7. We should have 7. 1, 2, 3, 4, 5, 6, 7. Okay, fine. And d over x minus e to the I pi. I'm cancelling the 7 out. Fitting these is the hardest challenge of this video. The computation is not even the hardest thing. Plus f and the second last factor. And then the very last factor. I just want to write these down so that we know what alphabet is associated with what factor. Okay, and now how do we find a? Well, for doing that, and again I'm choosing a slightly better color. To do that, I'm gonna cross multiply the terms on the right hand side. So I'm trying to get a common denominator. So if I try to do that, the common denominator on both sides, or at least the right hand side, will be sort of a product of all of these individual factors. And if you remember, all of these individual factors multiply out to give you this. So I'm going to have 1 over 1 plus x to the 7th on the left hand side. And with alongside a, if you do a cross multiplication, you're going to have all the factors over here on here, except x minus e to the I pi over 7, which is the first factor. So you're going to have everything but that. And how do you represent something like that? Well, you write the entire thing and just divide out whatever is not there. And I can do a similar approach for b. So the entire thing divided by what's not there. So same thing with c. And d. Yeah, writing this is a real pain, honestly. I'm just doing this so that people don't have too many problems in the comment section understanding, because I got some really weird suggestions that I did not even feel like commenting on because they were just so weird. Things like, why can't you do trig substitution? I mean, it's obvious that the person who suggested that, I don't want to take names, did not review their chain rule or reverse chain rule properly, especially with integrations like these. And now I'm going to divide, and remember this was all in the numerator. The common denominator is still a product of all of these things, which is precisely 1 plus x to the 7th. So I can cancel that off from both sides. Upon cancellation, we realize that 1 equals all of this garbage, this numerator garbage. So how do we find a? Well, for this, we're going to use a heavy side approach. And this was the name of a guy. It's not, there's nothing heavy about this. But what we're going to do is we're going to take the limit as x goes to the first root. So it's to the I pi over 7. When I do that, Notice the denominator is non-zero for B, C, D, E, F, and G, while the numerator is zero because this, and we indicated this above, is a root of this according to this green star factorization. So all of these other things except A will go to zero, but A, to calculate A, we need to take the limit, or this first factor, we need to take the limit. So I'm just writing this out, and I'll start skipping steps going forward as the pattern becomes more and more clear. So now we have this 0 over 0 situation, so just L'Hopital rule, don't think twice about it. We have 7, x to the 6th, and x is evaluated at e to the I pi over 7, so raised to the 6, so e to the I 6 pi over 7. And then the denominator sort of differentiate out to give you 1, so you don't need to worry about it. And a just becomes simply 1/7 e to the negative I 6 pi over 7. That's it. That's it. That's literally it. Because everything else just went to 0, right? I showed that because as long as the denominator is non-zero, which it is for this first root, which are the roots are distinct, we don't need to worry about any other L'Hopital rule going on. The only L'Hopital rule is here for A, because we had a 0 over 0 situation. To find B, you do a similar thing except take the limit as x approaches e to the I 3 pi over 7 to find B. And by the same logic as before, everything else goes to 0 except the B term for which you need to do L'Hopital's rule. So B and then this limit. Okay, I'm directly going to write the answer. The whole calculation is pretty identical, except now we have 6 times 3 e to the I 18 pi over 7. All we have to remember with the negative, all we have to remember for things like this is to take it, is to sort of consider the remainder when you divide by 14. Because we want even multiples of pi, even multiples of 7 with the pi multiplied with them will just become e to the I 2 pi raised to some power. E to the I 2 pi is just 1. To make this more clear, we have e to the I 18 pi over 7, right? The negative. You can write this e to the I negative 14 pi over 7 e to the negative I 4 pi over 7. Notice this becomes e to the I negative 2 pi, which is still 1. And this is what we're going to have finally. So I can just write this as e to the negative I 4 pi over 7. And remember, this doesn't always have to be 2 pi. It can be any multiple of 2. So so that's why I'm saying even multiple of 7 or any multiple of 14. So that's where the modularity comes in. So we can at least reduce them down. But when I'm going to generalize this, and yes, I'm going to generalize it in this video, I won't really care about like breaking down or simplifying these factors because it's hard to see for it when in place of 7 you have an n or a k. Now for C, you do a similar approach except take the limit as x goes to e to the I 5 pi over 7. So you have 1/7 e to the negative I believe 30 pi over 7 because 5 times 6 from the derivative. This becomes 1/7. Closest multiple of 14 is 28, so the remainder is 2, so 2 pi over 7. And for D, nothing changes. We have e to the negative I 6 pi because we have an I pi factor, and 6 is a multiple of 2, so this just becomes 1. So you just have 1/7. For e, when you take the limit for that factor, for that root, you have 1/7 e to the negative I believe 9 times 6, you have 54 pi over 7, but in this case, 54 falls behind the closest factor to 14, which is 56. So we're going to have to subtract an extra 2, so that's minus and this minus become a plus. You can do this, do like a rough division. You can do something like this. So 56 pi and plus I 2 pi over 7, which if you work this out, you get negative I 54 pi. And this is 8 pi. 8 is a multiple of 2, so that's like e to the I 2 pi cubed is just 1, so you get this. These are just small things that I'm just implementing so that those phase factors, those angles aren't really crazy. For f, nothing changes. 1/7 e to the negative I think 6 times 11, so 66 pi over 7, which we can reduce down further to 4 pi over 7. The closest factor of 14 being 70. And then for the last one, when we take the limit as x goes to e to the I 13 pi over 7, so we have 1/7 13 times 6, which is 78 pi, which you can also reduce down to 6 pi over 7. Notice the nice symmetry between these factors. We have negative 6 pi over 7 and then positive here, negative 4 pi over 7 positive here, negative 2 pi and positive, and then this extra factor that acts as like the middle of the symmetry. That's one good observation. Thing with complex numbers is that, especially if you write complex roots, the complex conjugate is also a root. So if we would have reduced these angles down slightly, we would have gotten this sort of symmetry right here when we wrote these factors down. We could have easily, done that kind of reduction up there, but I didn't bother with that. Okay, so what's left is integration, because now we've split them up. So when you integrate, integration is not that bad because we have linear factors and constants with respect to x. So if all of those linear factors just become corresponding natural logs with absolute values. I've been chastised before for not putting an absolute value, and I argue that it's just a domain that sort of considered, but I'm going to put absolute values. And it is important to put absolute values, at least for what I'm going to do later. So again, quickly change the color. To get those natural logs in. And I don't mind writing each of those factors because that's the final answer. So for A, we have the first factor of 6 pi over 7. Natural log absolute value of x minus e to the I pi over 7 plus 1/7, I believe e to the negative I 4 pi over 7 as the b factor with the natural log of x minus e to the I pi, 3i pi over 7. Distracted there for a moment. Plus, we have a lot to write. 1/7 e to the negative I 2 pi over 7. See, kind of like decreasing by 2 pi. That's a nice symmetry we have there. Meanwhile, these increase. So we have 5 pi over 7 plus 1/7 natural log. This is the best factor, x minus 1. Is I think this should be a plus 1 though, because factor was minus 1. So minus will be a plus. Plus 1/7 e to the I, 2 pi over 7 natural log absolute value of x minus e to the I, 9 pi over 7, 1/7 e to the I, 4 pi over 7, natural log of x minus e to the I, 11 pi over 7, and then I believe the last term, the 7th term, e to the I, 6 pi over 7, natural log of x minus e to the I think it's 13 pi over 7. Yes. And again, for the when we had the quintic case, for when we had instead of 7 we had a 5 here, which was a really famous video of this channel. We massaged terms and we got something that looked a little more like a real expression. Here the problem is I'm doing it more generally, so massaging, I'm not doing the massaging for these terms. But if you were to massage it, it's going to be horrible. You can even try some other graphing calculators, other software, some tools to see this or expand this or simplify this and sort of get rid of these imaginary factors like this. But this answer is pretty valid. And of course, don't forget the most important aspect of this, the constant of integration, because it's indefinite integration going on here. Now, what if, now just taking a step back, what if we were to sort of try to generalize this approach? Because we know how these things work. We can generate roots. The factorization for something like this was, say, n equals 1 to 7, x minus, this is a product, e to the I, 2n minus 1 pi over 7, because if you plug in n equals 1, we have I pi over 7, n equals 2, 3, I 3 pi over 7, so everything matches, and n equals 1 to 7, we have 7 roots generated this way. So if we had something like a k, all we do is just replace appropriate things. So x minus e to the I, 2n minus 1 pi over k. And then if we want to sort of generate these factors of partial fraction decomposition, remember what we did? We took the derivative. So that 7 was the power. And we're basically taking the root, raising it to the negative leading term, or in which case this was a 7. We're going to call this a leading term. So we took a power, raised it to the negative leading term minus 1. And we did that for each and every root. So let me just write a general structure, 1 over leading term. So in this case, it's going to be a k, that's the leading term. And then root raised to the negative, because we sort of like take the reciprocal when we divide. Leading term minus 1. That's the general structure, and we're summing over these because we have to sum over each of those 7 roots. In the case where we have a k, we have k roots. So if you sort of do this general observation, you're going to have as your integral, your antiderivative, 1 over k outside, because if you notice we had 1 over 7, that was the same for all of these regardless, and we have again this algorithmic form for it. And we know what the roots should look like because of this factorization here. And what we now have to sum because of partial fraction decomposition. We converted a product in the denominator into a sum. N equals 1 to k. We have e to the negative I, 2n minus 1. That's your root. Pi over k. This is actually a root. Raised to k minus 1. That's like multiplying in the power with the k minus 1, according to this algorithm. And then don't forget the natural log of x minus that corresponding root. So e to the I, 2n minus 1 pi over k. This is a really compact form, and of course the constant of integration c. This is the most compact form. I believe is a really nice solution. Again, you can simplify this or maybe complexify, make it harder by expanding and massaging terms and getting rid of these imaginary factors, but this is the best I can give you. I don't want to take an approach like we did for the quintic case, because factorizing that out may be hard. The factors might be really crazy rational numbers, and that is if they're real. They might just be imaginary because fundamental theorem of algebra sort of works in the complex plane. You need to have a complex domain for you to actually have all those roots. The roots could be complex, in which case they come in pairs, the complex and the complex conjugate. Proving that is pretty easy. Let's do a sanity check on a fresh page just to make sure that this formula is actually working. Okay, so this is the formula we have. Let's test it for k equals 2. So we have this simple integral, which we informally know is inverse tangent of x plus c. I mean, it might worry you that we have inverse tangent and we have natural logs here, but don't worry. We'll figure something out. We're strong when united. So let's just plug everything for k equals 2 in this formula. So we have dx over 1 plus x squared, a 1/2 factor, and then sum n equals 1 to 2, e to the I, 2n minus 1, pi over 2, and then 2 minus 1 is 1, natural log of x minus e to the I, 2n minus 1 pi over 2 plus c. So just write individual terms of this sum down. So 1/2. So when n equals 1, we have a 1 here. And I believe that there's like a negative that we forgot. Yeah, there's a negative there. So e, we have a 1 for n equals 1. Negative I pi over 2. Natural log of x minus e to the I pi over 2. That's fair enough. Plus 1/2. This is for n equals 2. E to the negative I 3 pi over 2. Natural log of x minus e to the I 3 pi over 2. Fair enough. Nothing is too bad until now. E to the negative I pi over 2 is negative I. This is x minus I. 1/2. Well, this without a negative is negative. So with a negative, that negative will become a positive I. Natural log of x minus and minus will give you a plus I plus c. Of course, you can plot this out on the complex plane and notice that 3 pi over 2 is like on the bottom imaginary axis. So that's why you get a negative I there. So we have I over 2 using that properties of natural logs, absolute value x plus I over x minus I. So what's the concern? The concern is that we have an inverse tangent here and we have a natural log here. So how do we deal with that? It's simple. Set y equals inverse tangent of x. X is tangent of y. Well, tangent is sine over cosine for the same angle. Sine, use the Euler's identity. Notice the 2's will cancel out because we had them in the ratio. We have this extra factor of like I in the denominator that will become negative I in the numerator because of the sign. The cosine didn't have the I factor. And then all you can do, sort of get rid of the negative power, e to the 2iy minus 1, e to the 2iy plus 1, and that's x for you. We can try to make y the subject of the equation. So 2iy e to the 2iy times 1 minus 1 over 1 minus x, sorry, 1 minus I times x minus ix minus 1 equals 0. So 2iy, taking the anti-log on both sides, ix plus 1 over 1 minus ix. So y is negative I over 2. Natural log, we can divide by I in the argument, so that we have x plus 1 over I, which is negative I, over negative I, negative x. But since we have an absolute value, you can sort of ignore the inner negative. So we have x minus I over x plus I. And what was y? Y was the inverse tangent of x. So we indeed have whatever we had here is indeed the inverse tangent of x. You can just check. Except we forgot to do a last step. Suck the I in, flip the numerator and denominator of the inside of the natural log, and that is precisely the form we had here. So this is indeed the inverse tangent of x plus c. Absolute value makes us sort of, that's why absolute values are necessary, note to self, note to everyone else. And this is the kind of massaging that is needed for higher and higher terms. It gets complicated. For k equals 2 itself, we had so much work relatively to do. Imagine for k equals 3, k equals 5, k equals 7. So much massaging to do. We don't even know what kind of function. The function might not even be simple, like a simple inverse tangent. We may not even have one function. We'll have a combination of them, and that's probably what happened. If I remember the result for k equals 5 correctly in that famous video, we had a bunch of inverse tangents and natural logs. Those were the dominant terms. That's because of this. The unmassaged terms become natural logs, stay natural logs, with probably real parts. And the massage terms become some crazy inverse tangents. So I rest my case. Hope you enjoyed the video. This is the best I can do. Please like and subscribe to my channel, guys. Make this video as famous as that one, if not more. Stay tuned for more content. In the meantime, stay home, stay safe, keep doing math, and peace out.